Okay, we're all set with our word vectors. We're ready to do some classification. As I've said earlier, we are going to be starting off by classifying IMDb reviews by sentiment. So whether they have a positive or a negative sentiment. A simple way of evaluating model performance is through the cost. So you, on your held out data, on your validation data set, you want to have the lowest cost that you can get, but that doesn't translate to much in the real world. Another simple metric for measuring the performance of a statistical model is the accuracy. So that's, let's say with these movie reviews, if the probability output for a given review is above 0.5 out of 1, we could say that that's our threshold for saying this is a positive review. But that's a little bit simplistic as well. That kind of single threshold in the middle doesn't get at all the nuance of the predictions that are being made across the spectrum from 0 through 1. And it's kind of nice to know that a prediction that's typically of 0.1 is less likely to be a positive review. So the ones near 0.1, these are the kind of most negative reviews, or all the way down to 0. Something at 0.3, maybe it isn't as negative. Something at 0.5 is right in the middle. And so as an example, if the only metric we're worried about is accuracy, then a review that is assigned a score of 0.49 is barely different from a review of 0.51, yet we're saying either that's either a negative clearly or a positive clearly case. It doesn't seem very nuanced. So a slightly more complex metric that I really like is the area under the curve of the receiver operator characteristic. This is a single value that represents a model's performance across the whole range of outputs from 0 up to 1. So let's go through an example of how we calculate it. I've got a little toy example here. So let's say the true state of the world, we have two possible outcomes. We have negative reviews and we have positive reviews, zeros and ones. Our model also makes predictions of negative reviews or positive reviews. So if the true state of a review is positive and our model predicts it as positive, this is a true positive. If the true state of the world is negative and our model predicts it as negative, this is a true negative. It's also correctly classified. Now, if the true state of the world is that this is a negative review, but our model predicts that it's a positive review, then this is incorrect. This is a false positive. Likewise, if the true state of the world is that this is a positive review, but our model says that this is a negative review, then this is a false negative. With me so far? That should be pretty clear. So I have, for a dummy example here, let's say that we have 4 movie reviews that we're testing our model on. Now, when we actually get to the real data, we'll be testing on 25,000 movie reviews, but I don't really want to hand calculate through 25,000 different numbers. So let's just use a toy example with 4. So let's say that we have 4 reviews. 1 is negative, 2 is positive, 3 is negative, 4 is positive. So we have an even balance in the real world. And let's say that our model outputs a 0.3 for this review, a 0.5 for this review, a 0.6 for the third review, and a 0.9 for the final review. So in this instance, the model is pretty confident that this is a positive review. In these middle instances, it has a kind of a middle confidence. In fact, for this one, it's right on the boundary, halfway through between 0 and 1. And for this one, it thinks that this is likely a negative review. So to calculate our area under the curve of the receiver operator characteristic, we pass over all of the possible values and we set it as a threshold. So that'll make sense as I go through it in a second. So we start off with the lowest value. So we can pretend that our threshold is right here at 0.3. So if we said that 0.3 is our threshold and everything at 0.3 or lower is a negative prediction, that means that the model's at that point saying that this is a negative and everything above it is a positive. In that particular circumstance, that means that it's correctly classifying this value as a true negative. So the true state of the world is that this is a negative review, and the model is predicting a negative review, so this is a true negative. In the next case, the model is predicting that this is a positive review, and in fact it is, so this is a true positive. It gets that right as well. In this instance, however, it is incorrect because the true state of the world is that this is a negative review. The model has predicted it as a positive review, and so this is a false positive. And then finally, this last one here, this is the same case here. It's a true negative. It's a 1 and a 1. So then we move along. So that's at a threshold of 0.3. Then we examine at the next threshold. So let's set the threshold to 0.5. So you do this for, if we had more data, you'd have more possible thresholds to iterate over. Here we only have a handful. So at 0.5, we do the same thing as we did before. We say that everything at 0.5 or lower is a negative review, and everything above that is a positive review. So now, this is still a true negative. This one, which at the 0.3 threshold was a true positive, is now misclassified, and this is a false negative. Our next point here is still a false positive, and this is still a true negative. So we have one last column left. So our last threshold here is 0.6. There's no point in doing it at the 0.9, and I'll explain why in a second. So for our final column here, we are setting the threshold at 0.6. We're saying that all of the reviews at 0.6 or lower are negative, and the one above is positive. Now you can see why there's no point in having the 0.9 as a final threshold, because we're assuming that this data set has some positives and negatives. It wouldn't make sense to have a test set that only has one class. So these are all of the possible thresholds that we've now accounted for. Let's see how the model performs at this 0.6. So again, this true negative is correct. Again, it's correct about this true positive. Oh, I mislabeled these. True positive. This is still a true positive. And now, at this point here, the model is saying that this is a 0. In the real world, it's a 1, so this is still a false negative. And for this 0.6, this is being predicted as a 0. It is truly a 0, so this is another true negative. Now, for each of these columns, we calculate the true positive rate and the false positive rate. So there's a simple formula for that. So the true positive rate is equal to all of the true positives that we have divided by all of the true positives plus our false negatives. And then the false positive rate, which we have over here, we'll get to this diagram in a second, is all of the false positives divided by the false positives plus the true negatives. So now we're distilling all of this information into two metrics for each of these values. So for the true positive rate at all of these three columns, we have 2 positives, 2 true positives, divided by true positives plus false negatives. We don't have any false negatives, so we're 2 for 2. So this gives us a value of 1. For our true positive rate here, we have 1 true positive divided by 1 plus 1, 1 true positive plus 1 false negative. So this is 1 for 2 for 0.5. And then in this final column, we still have 1 true positive divided by true positives plus false negative. So this is still half as well. So that's still equal to 0.5. And then finally, our false positive rate. In this instance, our false positives is, we have 1 of them divided by our false positives plus our true negatives. We have 2 of those. So 1 for 2, this is a 0.5. And then in this column, we have 1 false positive divided by false positives plus true negatives. This is still 1 over 2, so that's equal to 0.5. And then in the final column now, number of false positives, we don't have any false positives, so it's 0 divided by our false positives plus true negatives. We have 2 true negatives, so now this is 0. The beauty of this area under the curve of the receiver operator characteristic value is that now we can summarize these true positive rates and false positive rates across all of these levels into a single value. So we do that over here with this plot. So for each of the thresholds that we have 3 thresholds, we're going to create a dot. So our coordinate for the first dot is on the true positive rate axis. It's going to be all the way up at 1. And the false positive rate is going to be at 0.5. So a false positive rate of 0.5 and a true positive rate of 1 brings us to a point right here. For this second one, we have a true positive rate of 0.5 and a false positive rate of 0.5. And so that brings us right into the middle. 0.5 and 0.5 is right here. And then for our final dot, we have a true positive rate of 0.5, so here, and a false positive rate of 0, so that's here. And so that brings us to this coordinate right here. Then, to calculate the area under the curve created by this shape, we join the points together, and there's implied points here in the corners. So we end up creating this curve that has this shape. Now, if we had more thresholds, this would look much more like a curve as opposed to this staircase that we've created here. But the theory works the same way. So we want to calculate what the area under the curve is here for this whole space, and we can see that the area under the curve is 3/4 of the space. So therefore, our area under the curve of the receiver operator characteristic is equal to 0.75. The reason why I drew a dotted line here along the diagonal is that if our model were performing at chance, you would end up having a area under the curve of the receiver operator characteristic of 0.5. So 0.5 is about the worst you could perform. If you were a dart throwing monkey, that's where you would end up. These particular results are decent. 0.75 is a decent score. Obviously, the more complex the problem, the harder it is to get a high score here, the harder it is to distinguish positive cases from negative cases. So there you go. We've talked about the confusion matrix, which is this matrix right here. We've talked about how we go across all of the thresholds that are output, that are predicted by our model, to calculate true positive rates and false positive rates at each of those thresholds. And then we can combine the true positive rate and the false positive rate together to get a sense of a single metric, an area under the curve of the receiver operator characteristic that is in one figure, giving us a sense of how well our model is performing across the entire range from 0 to 1. If it were doing perfectly and we're classifying all of the zeros and all of the ones exactly accurately, then we'd fill up the whole space and we'd have a score of 1. In practice, these curves end up looking not like staircases because we typically have far more than 3 possible thresholds. And so we end up with some shape, kind of a round shape like that. And that's probably about a curve of 0.75. As the curve takes up more and more of this space, it could be 0.85, 0.95 of all the area under the curve, and a perfect score would be taking up 100% of this space. So with this metric, we can evaluate the performance of our IMDb sentiment classifier. In the very next sublesson, we are going to be writing some code to do that sentiment classification.